Imagine a particle in one-dimensional space, which is moving towards the right. And in this case, the right is the positive x direction. So the velocity of that particle, which I've called v1, would be some positive number. And that's really all you can say about this simple system. But now, what's more interesting is if you introduce another observer, which is also moving. Now, even though the particle is still moving to the right with v1, and so it has a positive velocity, the observer is also moving to the right at a velocity that I've just called v. Since this velocity is positive and this velocity is positive, you could say that from the perspective of this person, this particle would have a lower velocity. You can imagine that this arrow of velocity kind of cancels out with this velocity arrow. And so from the perspective of this person over here, the velocity of this particle, which I would call v1 prime, as indicated by that dash, would be equal to v1 minus his own velocity, which is v. And now the next scenario is very similar, except the person is moving in the opposite direction. Now you could say that since the person is moving in the opposite direction of the particle, the speeds would add together. This person is going this way, the particle is going that way, and so they're moving away from each other at an even greater speed. But even though the speeds should be added together, you have to keep in mind that this velocity now is negative, since this is the positive direction. So the speeds add, but the velocities still subtract. And in this case, v1 prime is still equal to v1 minus v. And that's a rule that holds in general, certainly in one-dimensional space. The velocity of anything from the reference frame of a moving observer, moving at velocity v, would always be the velocity of the particle from an outside observer minus the velocity of this person that is also moving. The same is true for the two-dimensional case, where velocities are represented by vectors instead of single numbers. This is because points and velocities can move in both the x and y direction, and so to encode the way they move, you have to have more information than just a single number. A similar equation is true. However, instead of v1 prime being equal to v1 minus v, you would have to use their vector versions. So instead, v1 prime as a vector is equal to v1 as a vector minus v as a vector, where this v vector, again, is the movement of the moving person. And so there are a few ways you can visualize this vector subtraction. One way, pictured here, is to imagine the v1 vector being drawn as this arrow, and then taking this vector and attaching it to the base of that vector. And then the resultant subtraction would be the vector that goes from the head of this vector to the head of this vector. A similar visualization can be done in this other case, where you attach the v vector, but first invert it, to the head of the v1 vector. And then, in this case, drawing from the base of the v1 vector to the head of the v vector gives you the v1 prime vector. And you can see from these two diagrams that they are the same. Now what I want to do is look at how this subtraction, which is actually called a Galilean transform, affects the momentum and kinetic energy of a group of particles. So you can see here I've drawn 4 particles, but there's nothing special about the number 4. And I've labeled each particle with a mass and a velocity. For example, this is particle 3, and it has m3 and v3 as masses and velocities. And so for any individual particle, the momentum will be its mass times its velocity, and of course momentum is a vector, whereas kinetic energy is a scalar, and it's 1/2 times its mass times the magnitude of its velocity squared. This means that momentum has a direction, and if you have 2 objects with opposite momentums, they can cancel out. But kinetic energy is only a magnitude, and if 2 objects are traveling in opposite directions, their kinetic energies don't cancel out, they actually add up. The I here is just a subscript that shows the index of each of these particles. So for example, for particle number 3, I would be 3. And now, ignoring the effects of the moving observer, which is moving at a velocity of v, the total momentum as a vector would be the sum of all the individual momentums of each individual particle. And since the momentum of each individual particle is its mass times its velocity vector, the total momentum is the sum across all the indexes, where n in this case is the number of particles. Similarly, with kinetic energy, it's the sum of the kinetic energy of each individual particle. And kinetic energy is 1/2 mv squared. You can factor out the 1/2 to the outside of the sum, and you end up with 1/2 times the sum of the mass times the magnitude of velocity squared. These numbers show the total momentum and total kinetic energy when you ignore the effects of the Galilean transform. Now the question I want to ask is how the Galilean transform, written over here, affects the total momentum and total kinetic energy. For example, with the total kinetic energy, you could write that the change in kinetic energy, which is delta Ke, is equal to the final kinetic energy minus the initial kinetic energy. And you can see that the expressions before and after the minus sign are almost identical, except in this case, you're using Vi prime, and in this case, you're using Vi. And of course, you can rewrite that by expanding out what Vi prime is, and also grouping the two sums together into this final expression, where the total change in kinetic energy is 1/2 times the sum of all the masses times the final velocity squared minus the initial velocity squared. This is not too surprising, since there's no neat way to simplify this expression over here. The momentum, on the other hand, can be simplified. This is because to calculate momentum, all you need is a simple multiplication. So in this case, the total change in momentum is the sum of all the final momentums minus the sum of all the initial momentums. And since this Vi prime can be expanded out into Vi minus V, you can then actually just do the subtraction inside the sum, ending up with the sum of all the masses times the negative V. And V in this case, of course, is the velocity of the observer. And now if you let the total mass be m subscript t, where t is just standing for total, then you get a very neat expression for the overall change in momentum, which is negative times the total mass times the velocity of the observer. And this makes sense, since momentum works so well with multiplication and addition. It just makes sense that algebra would also work well with it. And so you can almost treat all the particles as a collective, and by moving away or towards the group of particles, you change their apparent total momentum.